Hello, this is Titus Dudden for Project 6 of CpE 3110. For the first circuit we have here, this is a input-output device priority state machine. So like we've seen previously, this is just a state machine that has state logic, which then it has our output logic, which just pretty much signifies to LEDs, which tells us what is happening in the protocol. And since it's pretty similar to other projects that have happened, I'm going to go ahead and move on. With this, what's happening here is there is send or receive. The IO is either ready or it isn't. There's a start, a reset, clock, and then all of these outputs, which pretty much just show me what's happening. And then these are the states. So we can see that whenever the IO isn't ready, it keeps cycling through these states, but once the IO goes ready, it cycles further into states. Since the S is 1, let me check the code to see which one that is so that I do not misspeak. When S is 1, the CPU is sending data. So what ends up happening here is this goes high, the IO is ready, start is high. So then right here, we can see that this moves into the next state, into the next state, into the next state, which in these states, the data bus, the address bus, and the control bus are all high, and then which we get a high signal showing that the data was sent. And then in this case, we are doing the opposite where SR is low, the IO is ready, and it cycles through where the data bus has nothing for the first cycle, then it takes in, it is sent data, it continues to receive that data, and then once that data is received, the receive goes high, and then the rest goes low. So then moving to the hardware test, we can see that I'm going to go ahead and push it into the first state, and I'm going to leave the IO low. So as you can see, it just cycles back and forth through the first few stages. Once I set this IO high, so the IO device is ready, we will get an output where this is the address bus, control bus, and then data bus. And then now this has, since this is low, it has received. And then we can set this high. It will cycle through the similar cycle. Oh, I overshot it. And we can see that now the sent LED is high. We can move over to Cordis, because I skipped that. This is the block being used. And then this is what the RTL compiler believes it ought to look like, where we have all of our inputs running through state machines, running through registers. And that is everything for this circuit. Okay, moving on to the second circuit for this project, we have a forward moving daisy chain, which is all of this right here. Pretty much we have the interrupt, which is where the interrupt will go high if any of these is the case. We have a bunch of reset logic just so the circuit doesn't break itself at any point. The acknowledge signal gets sent high when the interrupt signal gets sent high. And then this is the interrupt logic, where the interrupt is 1 if acknowledge wire is high and the interrupt of 1 is high. This is high when the acknowledge interrupt 2 is high and interrupt 1 is low, and so on and so forth for interrupt 3. And then we just have some LED assignments. So nothing super complicated. Moving on to the waveform, you can see, let's see, you can see right here where interrupt 1 goes high, so LED 1 goes high, so the interrupt and acknowledge both go high. Interrupt 2 goes high, LED 2 goes high, interrupt acknowledge goes high. And you can see right here where interrupt 1 and interrupt 2 both go high, you can see that only LED 1 goes high. Interrupt 1 drops, LED 2 goes high. And we can look at Cordis for the block. So this is the block, nothing much to look at. And this is the RTL viewer right here. So we have our reset, our data points, and then just the simple logic. Moving over here, we can see that if I have my reset high, it doesn't do anything, no LEDs light. But if I set my interrupt 1 high, you can see that the acknowledge and interrupt both go high. If I set my interrupt 2 high, nothing changes. Interrupt 3 high, nothing changes. If I drop this, interrupt 2 is the highest priority, so interrupt 2 stays high, and then it moves to interrupt 3. So as you can see, the highest interrupt key maintains the highest priority for this circuit. And that is everything for this circuit. For the next circuit in this project, we have a daisy chain backwards system, which is, it's more complicated and there are a lot more errors that can occur. And based on a diagram I have right here, you can see we have to function as the device controller. So we as people are this little brain. We have to send out this signal, this clear signal, this address signal, and that's what lets all of this function. So going back here, we have all of our inputs, we have our outputs, which are mostly for observation. We have assignments for observation. We can see that this is the OR logic for the interrupt. This is the acknowledge logic. And this is what the interrupt wire is actually equal to, which is the OR. To scroll down, as you saw in the diagram, we are using flip-flops for this. So this is the IO device. This is going to be our first always block, and then the AND gate logic and the D1 logic. After that, we have this will be the acknowledgement. This will be the acknowledgement always block, and then these two down here are the same thing, but for the second set and third set of IO devices. And then down here is the final AND logic, the error logic, which is basically saying if the AND gates here, so this AND gate will be acting on this data bus, this one to this one, this one to this one. For this, it's saying that if any more than one are active at any time, the error will go high. That's an observation assignment. And then this is just an assignment so that we can see the data bus in use. Moving to the waveform, the main thing I'm wanting to show in this is this right here, is the error. So you can see we have address 2 and address 1 are both, So we have signal 1, signal 2 are both set high. And we can see that interrupt 1 and interrupt 2 are both set high. And due to this, the error runs high, which since we can't have more than one acting on the data bus at a time, we have an issue. And this system is inherently flawed, and this is why we have this project, to show the inherent flaw in backwards daisy chaining. And we can go ahead and move to Cordis from this.
So the next thing what I would like.
This is the block here where we have all of our pin assignments. So again, not much to show. And this is the RTL viewer right here, which is showing what the compiler would turn this into, being logic, actual hardware. We can move over to the hardware test now, speaking of, and I already was fiddling around with this, so I'm gonna go ahead and reset it. We can see that if we have address 1 high and S1 high, we can move forward a clock cycle, and we can see that interrupt and acknowledge both run high. Then we can see this is interrupt 1, and then you can see that the data bus is in access. And then if we set this high and this high, this should activate the second one, which then this is now interrupt 2, and now they're both acting on the data bus at the same time, which then sends up this error signal. And what we did here is we ran R1, which is high, which kills the interrupt signal. And then we can see the error runs low now because only interrupt 2 is interacting with the data bus. That is pretty much everything for this, and we don't need that right now. So that is everything for this circuit. For the final circuit in this project, we have the multi-port memory. So I'm going to move over to Model Sim and show the code for that. So this is the code here where we have our data outs, our data ins, our enables, our writes, and our clock signal. We have our address choice and an error signal as well. We have our internally built RAM, and we have the port logic for port 1 and port 2, where it's saying that if the enable is high and the write, and the write is high, then the data will make it into the RAM, else we are just reading the RAM based on the address chosen. And then the same thing for the second port, just with additional variables. Moving on to the error, it looks messy, but effectively it's saying that if both of them are writing to the same place, you get an error. If one is reading and one is writing to the same address, you get an error, and vice versa. And that's gonna be it for the code. Moving over to the sim, we can see here, everything is set to 0. Right here, the data in is 0111, and then the data in is 1110 for the data 2. And they're going into separate addresses, and you can see they come up as the data out, and there's no error. You can see that the write goes low and the read is high, and the read is high for the second one as well. So we're reading these two pieces of information, no writing, and the error is not high. And then once we set the write high and we're reading both from the same address, we get an error signal, and then the additional cases further on. Moving to Cordis, this is the block diagram we have. These are all of our inputs, these are our outputs. This is oscilloscopes for time delay, and these are two different clocks. This is an integrated 50 megahertz clock, and this is a hand clock. This was used to determine time delay, and this is used just to show it. We can go to the RTL viewer as well, which is this absolute behemoth right here. So this is what the RTL, the compiler, believes the code would look like as hardware. And we can move on to the hardware test. So these two LEDs are lit up for no reason because the Altera board is silly, so we're going to ignore them. So we can see that the data in is going to be 001, and we're going to set the address to 0, and we can set the enable high and the write high. We will move forward a clock cycle and then set the write low, move forward another clock cycle, and we can see that it appears. And then we can also set the read enable high, move forward a clock cycle, and we can see that that appears on this set of LEDs as well. We can go here, we can set a different data point. We can set the write high, and as you can see, since this is reading from the same address and this is writing to that same address with a different piece of information, that error light now goes high. Whenever we pull down this signal, we can write it, we can pull down the write, and then we can read it. And that is perfectly fine. And of course, both of these can be reading at the same time. So if I push these both high, no error. And if they are both writing, then we have an error. That is pretty much it for the multi-port. So it's just, you can send and receive two pieces of information at once. But if they are on the same address, it creates problems. Now we can move over to the oscilloscope. As you can see, this is the time delay. We had about 10 nanoseconds of time delay. And this is, let me go ahead and flip that right there. You can see this is what the clock signal looked like. Since it's 50 megahertz, it effectively just looks like a really noisy bar to us right now, since the times division is 2 seconds. And I can go ahead and check this right here. Let me make that a bit slower. So then if let's see if I can get this to work. So we will set this to 0. We will set that all to 0. I will make it so that it will write to 0. So everything is low now for the time being. And then I can make it so that it sends in a piece of data, and then we can see the delay here, which is how I produced that. And that is going to be everything for this circuit.